like I said, we are now in an interactive debugging session. We just stopped the program. We can actually continue the program if you want to see what that looks like. Right now, you'll see how we're not running right now. If I say continue, then we're going to keep continuing, and then I can stop it again. And now we stopped at line 750. Basically, we are in an interactive debug session where we have full control over the MCU. We came in through either 3 USB wires or some Ethernet wires or some Zigbee or whatever, and we've got full control over the MCU, like just as if we were using an in-circuit emulator. We can stop the program, start the program, change the program. We can actually modify lines of the program, and we support an edit and continue. So lines get recompiled, reintegrated into the program, and you can continue the change program from where you left off. Anyway, we can also, as we've seen, modify pins. We can examine and modify variables. We can also, we have a tilt variable that tells us where the accelerometer is right now, and basically it says we're at 1696 millivolts. And if we turn the board up on its end and recall that command and try it again, now we're at 2571 millivolts. So we have got live access to all the pins. We can control all the pins, we can read all the pins, we can control the variables, read all the variables. We're in a very powerful debugging session. We can set breakpoints, we can, do assertions, we can set watch points, we can, all sorts of really cool things right here for debugging this program. But we're not here to debug right now, we're here to look at the program. So let's list it. This is basic, remember? And we're going to scroll to the top, and then we'll go through the program, kind of section by section. So this is the start of the program. It's however many lines that was, 93 lines I think, or something like that. We start out by declaring some RAM variables. X and Y are basically just going to be the position of the ball at all times. XV and YV are going to be its velocity components, typically 1 or -1. P is the position of the paddle. Programs typically start out by declaring their variables, and then they're going to declare pin variables, which is basically they act just like regular basic variables, but they're bound. Instead of having RAM behind them, they actually have pin functionality behind them. So when you configure a digital output pin variable, when you modify that, the pin instantly reflects the modification. When you configure an analog input pin variable, when you read it, it instantly reads the instantaneous value on the A to D converter right there on that pin. So we have to interface first to the accelerometer. In order to do that, if you remember, the accelerometer has 3 inputs that have to be set before you can actually use it. Those translate into outputs on the MCU. Those are G-cell 1 and G-cell 2, which are the gravity sensitivity select, and the sleep pin. What we're going to do is we're basically going to bind a variable named G-cell 1 to pin PTC4, and we're going to configure that pin for digital output. A little bit down here, we're going to assign 0 to that, and that's basically going to lower that pin on the that output pin on the MCU. We're going to bind the variable G-cell 2 to pin PTC5, and we're also going to configure that for digital output. A little bit down here, we're going to again assign 0 to it, and that's going to lower the output pin. Finally, we're going to declare a variable named sleep, and we're going to bind it to pin PTC3. And this one's configured for digital output inverted. Basically, what that's saying is that it's an active low signal named sleep. And so, in the program, we want to be able to refer to all these variables in their positive sense. If you want to go to sleep, you say let sleep equal to 1. And this basically, the inverted basically says, you know what? Even though we're referring to all the variables in the positive sense in the program, by the time it gets out to the MCU, I want a go to sleep signal to be represented by a logic 0 instead of a logic 1. So when I set that to 0 here, that's saying I don't want sleep logically, so please put a 1 on the pin. Anyway, once we've got G-cell 1, G-cell 2, and sleep configured and assigned, then we can use the accelerometer at that point. So we can use the analog inputs of the MCU attached to the analog outputs of the accelerometer, and we can actually access that. So what we're going to do now is we're going to bind a new variable named tilt to pin PTB5, which is an analog input pin, and we're going to configure it for analog input, also inverted. Basically, analog input says, turn on the analog to digital converters and make sure they're running, and every time I access the variable tilt, make sure that I have the current value of the analog voltage on that pin in millivolts. Inverted basically says, what I really want is 3300 minus that value. So when the pin is at 0 volts, I want to see a value of 3300 in the variable tilt. When the pin is at 3.3 volts, I want to see a value of 0 in the variable tilt. It just makes the program flow a little bit easier. Anyway, so we've got the accelerometer configured. Now it's time to interface to the buzzer. To interface to the buzzer, basically we just need one pin. So we create a new variable called audio, and we bind it to pin PTF2, and we configure that for frequency output. That means, take that pin, turn on the timer that's on that pin, and program the timer so that, if the guy sets audio to 5,000, we've got a 5,000 hertz signal on that pin. If he sets it to 500, we've got a 500 hertz signal on that pin. If he sets it to 0, we turn off the frequency on that pin. Finally, one last thing to do. We've got all the pins configured. Now we need a virtual timer. You have up to 4 virtual timers. What we're going to do is we're going to configure virtual timer number 1 so that every 50 milliseconds it will call a paddle subroutine. Basically what we're going to do in the main program is we are going to manage the ball position in the main program. We're going to track the ball. We're going to figure out when it bounces off of things, figure out when the game is over, and things like that. Asynchronous to that main program, every 50 milliseconds we're going to call a paddle subroutine in order to track the paddle and to basically measure the accelerometer, figure out whether the paddle needs to move, and so forth. So on to the main program loop. So the main program loop is really 2 while loops, 2 nested while loops. Okay, there's an outer one and an inner one. The outer one basically, again, we auto run when the guy turns the badge board on, and the outer one is basically truly infinite. Okay, we're going to play this game over and over and over again until the guy turns the badge board off. Okay, the new one is basically the inner while loop is basically the managing an individual game. Okay, so we're going to stay in the inner while loop until the game is lost, and then we're going to break out, and then we're going to return to the outer while loop, and we're going to start a new game. So, new game initialization right here. What we're going to do is we're going to start out, we're going to put the ball in the upper left corner, we're going to set its velocity to 45 degrees down, and we're going to set the paddle in such a position that if the user doesn't do anything, he's going to hit the ball the first time. Then we have 2 statements that are special. Basically, we can run the exact same version of this operating system on the 51JM128, the 52221, the 52233. There are only 3 statements, two of which are these, that we've added to the badge board to make the badge board experience a little more badge board unique. And that is basically we've added the ability to manipulate the LED matrix. You can set and clear individual or groups of pixels on the LED matrix using the JM clear and JM set commands, and you can also scroll text asynchronously across the LED matrix using the JM scroll command. So what we're doing here is we're basically clearing the display and then setting just the pixel representing the current position of the ball. Then we sleep for 3 seconds, 3,000 milliseconds to give the user time to prepare, and then we begin the main game loop. The main game loop, basically we enter this on a new game, and then we're going to stay in this loop until the game is lost. All that we're going to do is we're going to clear the old ball position, then we're going to calculate the new ball position by basically adding the x velocity to the x position and the y velocity to the y position, and then we're going to basically go through our edge detections. So if we hit the horizontal edge of the screen, then we're going to bounce horizontally, which means we're going to invert the x velocity. If we hit the bottom of the screen, then we're going to need to do a couple of things here, right? First thing we need to do is we're going to check and see if the paddle was nowhere close, then we basically just lost the game. So we call the lose subroutine, and then we break out of the inner while loop, return to the outer while loop, and start a new game. Otherwise, if we didn't lose the game, but we were really close to the edge of the paddle, then basically what we're going to do is we're going to give this paddle kind of a 3D feel, and we're going to let the ball bounce not only vertically off the paddle, but horizontally as well. So we, again, invert the x velocity. Then, basically, if we've hit the top or the bottom of the screen, we need to bounce vertically by inverting the y velocity. This assumes that, if we're here, we haven't lost the game, so we must have hit the paddle. And finally, here we're going to set the new ball position. We computed the new ball position up above. We're going to set the new ball position, and now what we're going to do is we're going to wait a little bit before moving the ball again, so the user has a chance to react. But we're also going to beep. We want to beep every time that we move the ball. So we're going to set a 100 hertz signal for 100 milliseconds, followed by a 0 hertz signal for another 100 milliseconds. At that point, we go back and we move the ball again. So we're moving the ball basically once every 200 milliseconds. Half of that time, we've got the audio on. So that's basically the main program loop. Manages the ball position, figures out when the game is over. Completely asynchronous to that, we've got the paddle subroutine that's being called every 50 milliseconds by a virtual timer.